So as we've talked before, the main goal of, or the job of a muscle is to produce force that will ultimately cause something to move. So with a skeletal muscle, we produce force so that our body can move, right? And so we're going to talk about how that force production actually occurs in this video. All right, so here are our several objectives, but this shouldn't be too long. So we look at them all together. The factors that affect force production are things called like autogenic inhibition, activation of our agonist and antagonistic muscle groups, which we talked about a little bit at the end. That's where reciprocal inhibition comes in, at the end of the last video. Joint mechanics and muscle structure. So the first one is autogenic inhibition. So if you recall from earlier in this unit, we talked about muscle spindles and Golgi tendon organs. So the muscle spindles monitor length and rate of change of length. And so if the muscle lengthens too fast, feedback from the muscle spindle causes muscle contraction. Okay, so or in other words, the muscle shortens. Now during normal contraction, we don't want this. Okay, so you're going to be lengthening muscles like as you walk. Okay, when you have knee extension, your quads are going to shorten, but your hamstrings are going to lengthen. And so we don't want the spindles to inhibit the lengthening of those hamstrings, otherwise you're not going to be able to do anything. And so we have those motor neurons, the gamma motor neurons, and what they do is they basically inhibit the muscle spindles or prevent the muscle spindles from causing muscle shortening, and as a result, muscles are allowed to lengthen. Okay, so muscle spindle normally causes activation of a muscle, and when we activate a muscle, it gets shorter. But when you're just kind of going around doing your normal thing, you want your muscles to be able to lengthen so you can have some movement. And so those gamma motor neurons inhibit the spindles so muscle lengthening can occur. We call this autogenic inhibition. Then we've got agonist and antagonistic muscle groups. Okay, and so how does this affect force production? And the kind of the easy way to look at it is if I have greater activation of my antagonistic muscles, I'm going to have less agonist force. Or in other words, I'm not going to be able to really, there's not going to be a lot of movement. Less antagonist activation, we're going to have greater agonist force. So that reciprocal inhibition that we talked about, not on 5-1-1, but 6-1-1. Okay? And so just on that previous video. Okay, and so that's the second thing. So the third one, we get into physics here. And so some, many, most, all, I don't know, maybe none, have probably taken biomechanics or in biomechanics right now. And so I really like this quote. It's from Archimedes, famous old scientist, right? Give me a lever and a place to stand, and I'll move the earth. Give me a fulcrum, and I shall move the world. Give me a firm spot on which to stand, and I shall move the earth. Okay, and so this is just talking about levers and the power of levers. Okay, and so this plays right into how we move. So if you think about it from, I guess, an anatomical perspective, the bones are the levers, the joints are the fulcrums, and the skeletal muscles are the pulleys and the weights. Okay, and so we take these concepts or these I guess physics or biomechanical concepts, and we can apply this to force production. All right. Now, when we move bones, it's actually we're creating torque, and torque is just a rotational force. And so what we're doing is we're applying a force, and then we're moving something around an axis. Okay. So here's our axis. We apply force, and so just think of this as like your ulna or radius or whatever it is, you know, your arm, maybe just go that general or that big. And so we apply a force, and then you're going to, you know, if we have elbow flexion, we're going to say that's this way. Okay, we're moving around the elbow joint. So this is like our elbow. So I'm going to put elbow here. I really wish I had cool stuff like Khan Academy. Okay, now that force, that torque that we're applying is dependent on three things. One, how far away are we applying the force from the fulcrum or from that rotational point? Okay. Two, how much force are we applying to this point? And then three, what's the angle between basically your lever and the force? Okay. The greater the radius, okay, or the longer your lever, just think of this as lever length. So lever length, the greater the force. Okay, so some of you are probably old enough to remember a guy named Randy Johnson that was a pitcher. He threw gas, right? He threw 100 miles an hour before everybody was throwing 100 miles an hour. Well, one of the things that he had to his advantage is he was 6'11". Okay, so he's got very long levers, and so as a result, he could generate a lot of force. It was easier for him to generate force than it would be for someone like me. I'm only 6'3", right? Okay, and then the other thing is this angle. Now, an easy way to think about this is just imagine opening a door. So just a door that you have to push open. Okay, so like as you're walking out of the building, I think generally when you walk out, you push to get out. Okay, now, next time you go to a door where you just have to push it to go out, I want you to push at an angle as opposed to straight on. When you push straight on, you're going to generate the most force. But if you push at an angle, that's going to decrease the force. And then the other thing you can do is push closer to where the door hinge is. How much more force do you have to generate to open the door as opposed to if you push on the very furthest part of the door, part of the door that's furthest away from the hinge? It's a lot easier. Okay, and this comes back to physics. So it's how big is your lever? Okay, or in other words, how far away are you applying the force from the fulcrum or the hinge point, the door, or excuse me, the joint, that sort of thing. Obviously, how much force are you applying, and what's the angle between the fulcrum, or excuse me, between the lever and between the force. Okay, 90 degrees is best. So then we get into recruitment. And so recruitment, if you remember the size principle, we recruit muscles from small to large. Most muscles have multiple types of motor units. And so our slow twitch muscles are recruited fast. But the other thing that's important to remember is that they keep going, like they don't get tired. All right. And eventually, we can get to a point where we're recruiting nearly all of our motor units, okay? 100% recruitment appears to be impossible, just generally speaking. With electrical stimulation, we can get pretty close, but even then, it's difficult. And so depending on how trained you are, you might be able to recruit 95 to 99% of any muscle fibers in a single muscle, okay? But the more you recruit, the greater the force. Okay, so we can bring this back to a tug of war. The more people I have, the more force I'm going to generate. Well, how does this happen? Well, remember that each motor neuron or each motor unit innervates several muscle fibers. Okay, or in other words, each muscle fiber is innervated by a motor neuron. Okay, at rest, motor neuron resting potential is about -70. And so in order to have an action potential, we have to reach threshold. Okay, so something changes, membrane potential, we get to threshold, action potential occurs. So small motor units are recruited first because they have the lowest threshold. And this is a number I'm making up. This should say -60. It just, the minus sign got up there. Larger motor units are recruited later because they have a higher threshold. So maybe for those, you have to recruit, or the stimulus has to be -50. And so as a result, we can recruit the smallest before we recruit the largest. The last thing that I want to talk about on this video is the concept of rate coding. Now, rate coding basically just says the faster or the more frequent that we recruit a muscle or that we send an action potential, the more force is going to be generated. Okay? And so this is a big deal when you're getting into pretty intense exercises. So what happens here is that normally, and we're going to say that this is force on the y-axis and this is time on the x-axis. So normally there's force production right there. Okay, so we just have a stimulus, muscle fires once, and we're done. Okay, but, and this is not an action potential. Remember, this is not an action potential. We're measuring force. Okay, and so let's say we have another stimulus and we hit max and then we start to go down, and then we have another stimulus that goes down, and then another one, and then another one. We're not letting the muscle fully relax. Notice our force production is a lot greater. Okay, and so what happens is we recruit them more frequently, and then also we can get to the point where the motor units are synchronized. And what we mean by that is that they're firing at the same time. Okay, and that will also improve force production. Just again, go back to your tug of war and say that there are 10 people. When you line them up, everybody's got a number 1 through 10. And let's say that when you're doing this tug of war, that the people with the odd numbers pull, and then the people with the even numbers pull, and they're on the same team. Okay, what's that going to do to force production? It's going to minimize it, as opposed to if everybody pulls together, everybody generates force together, they're going to have, the sum of the parts is going to be bigger than if it's just half of them pulling at the same time. And so that's where we're going to end right now for force production.